Hello, and welcome to this session of the 2021 New Hampshire DOT ACEC New Hampshire Tech Transfer Conference, where we'll be talking about the replacement of two bridges on Interstate 91 in the town of Rockingham, Vermont, with spliced precast girders. I'd like to start off with some acknowledgments of the entire design build team, and that's of course with the owner, which is the Vermont Agency of Transportation. And first and foremost, the project manager, Carolyn Coda, and the resident engineer, Daryl Bassett. And the other names you see on the team here, the design build team, which was Reed and Reed of Woolworth, Maine, and HDR Incorporated. The design build project manager was John Phillips, and I was the design manager for this project. Here's a brief summary of today's presentation. We'll start off with a brief project background, talk about the project criteria, talk about the splice girder superstructure, the substructure of the project, move into design details, some challenges, and then finish up with a time for some questions. And now we'll talk about some of the project background. The bridge project site is located in Rockingham, Vermont. For those of you not familiar, it's in the southeast corner of the state. The twin bridges carry Interstate 91 over the Williams River and Green Mountain Railroad. Average daily traffic was approximately 6,900 in 2017 and is only estimated to increase to 7,000 by 2027. So there really isn't any need for significant future expansion for the foreseeable future. The existing twin bridges were constructed between 1963 and 1965 and consist of 4-span steel deck trusses. Each bridge has 12-foot travel lanes and 3-foot shoulders on each side. The bridges are 736 feet long. It was determined that a rehabilitation would extend the life of the bridges for only 15 to 20 years at a cost of about $20 million. It was also determined that a full replacement set of bridges with 100-year service lives could be provided for about $44 million. So the end result was that the life cycle cost analysis showed that replacement was the preferred alternative. VTran has listed the bridges in poor condition, with bridge inspection reports calling for full deck replacements. As you can see in the photos on the right, there's significant concrete spalling in the deck, soffit, and the columns. In addition, steel truss members and connections have structural section loss, and you can see those in the sections that I've highlighted. The top right photo shows spalled concrete where the deck reinforcing has corroded over time, and in the bottom left photo you can see sections of structural steel that have some significant amount of pack rust and advanced deterioration that are starting to lead towards load carrying restrictions. In the lower right hand picture you can see sections of spalled concrete again where salt that has corroded the reinforcing steel there has spalled off the concrete. Due to the extremely poor conditions of the existing bridges, VTrans released a request for proposals for 2 replacement bridges in November 2015 through a design build delivery system. The base technical concept included in the RFP was for the construction of 2 segmental box girder bridges. Each bridge was to consist of 3 spans. With 2 bridges, traffic control could be maintained by shifting the traffic between the 2 structures when work on one structure was being done. This allowed the new bridges to be built on the existing alignments. During the bid process, our design build team proposed an alternative technical concept that included twin 4-span precast post-tension splice girder bridges also placed on the original alignment. The Reed and Reed HDR team submitted our technical and price proposals in May of 2016. Our proposal had the highest total score of 88.6, which was approximately 10% ahead of the next bid. Our proposal did have the lowest bid price of $44.3 million. As you can see in the cross-section, the project widens each bridge by a total of 8 feet. You'll recall I mentioned earlier the existing bridges have 2 12-foot travel lanes and 3-foot shoulders. The proposed bridge adds 1 foot to the median shoulder and 7 feet to the exterior shoulder, bringing the bridge cross-section in alignment with the rest of the I-91 corridor in the area. Some of the advantages of our alternative technical concept over the base technical concept was that it improved inspectability, reduced the need for internal lighting, and the availability of local producers that could provide the structural elements. It is somewhat unusual for an alternative technical concept to come back with more spans than the BTC, but in this case it made a lot of sense. The proposed 245-foot main spans place this in the sweet spot for a splice girder bridge. Now personally, I'm a big proponent for the use of segmental bridges, but in this case, site characteristics made splice girders the optimal choice. The 4 spans allowed the main spans to straddle the Williams River and to span over the Green Mountain Railroad with plenty of setback. As you can see, it increased the setback from both. Also, there were experienced precast fabricators available that had already provided girders on another splice girder bridge in Vermont, so this lowered the overall risk for the project as well. Lastly, the span arrangement that you can see here allows for the use of 2 of the existing piers. They're shown in dashed lines on either side of the Williams River. We were able to use those piers as temporary supports for the erection of the haunch girders over piers 2 and 3, and this also reduced the overall cost of the project by not having to construct 2 additional foundations. The new bridges are each over 850 feet in length, and that's almost 120 feet longer than the original bridges. We'll now spend some time talking about overall project criteria. The request for proposals included several special requirements for the bridge design. One, first and foremost, was a requirement that the bridge design produce a bridge that had a minimum of 100-year service life without major rehabilitation efforts. It also had stainless steel reinforcement requirements. It required that all deck reinforcement, all bridge reinforcement, and any girder stirrups extending into the deck and all pier cap reinforcement be stainless steel. Also required stainless steel or FRP deck drains. Lastly, it required that the deck be a minimum of 9 inches thick and have 3 inches of asphalt with membrane placed on top. And it noted that utilities were not permitted to be anchored into the deck soffit areas. Let us now spend a few minutes talking about the splice girder superstructure. New England bulb tees, NEBT 79s, were modified for use on this project. Webs were thickened from a normal 7-inch thick web to 8 5 inches to accommodate 4-inch post-tensioning ducts. The hammerhead segments were made variable depth. 3 19-strand tendons were used. Dewey Dag System International USA is the post-tension supplier. Precast fabricators imposed limitations on girder segments due to plant and shipping restrictions. The designs were limited to keeping our segments less than 180,000 pounds and no greater than 10 feet high. On this slide, we can see some of the details for the precast splice girders. What is shown on this slide are the variable depth hammerhead or the haunch girders. The hammerhead segments shown here in elevation and section varied in height by extending the height of the bottom flange. The rest of the NEBT 79 stayed constant. This made for easy modifications by our precaster to their forms. As we saw earlier, there are 5 lines of girders at 8-foot spacing for each bridge. We did consider reducing the number of girder lines to 4 during the proposal phase, but stayed with 5 to allow additional flexibility during design. We evaluated this potential change against cost and risk benefits. If we had been able to go deeper than 10 feet at the pier sections, a 4-girder section would have been much more attractive for us. For the girder design on this project, the PG Splice component of the BridgeLink software suite was used for the design. The new version of PG Splice, which had recently come out, was a giant leap forward, and now it has the ability to handle multi-span splice girder bridges, variable depth sections, time-dependent analysis, as well as perform load ratings at various stages. Design began actually while the program was still in beta testing phase, so our engineers actually worked with Washington State DOT to refine some of the program features. Since we were using this at the beta version, we actually performed a separate design team independent design check using LARSA, and also used ConSplice as a check during the preliminary phase. Various design checks were performed at different stages during construction and service, starting at the casting bed and all the way through service load and checks all the way up to the 100-year service life. It resulted in 32 different design cases per girder. There were also other considerations that were checked outside of BridgeLink software due to the limitations of the software. These included stage deck pours, which is essential for the correct camber calculations, strand elongation estimates, and the temporary support reactions necessary for the construction phases. We're now going to move on and talk about the bridge substructure design. All the piers, except one, are founded on driven H-pile supported foundations. The 6th pier was placed directly on bedrock. Interior piers ranged in height from 100 feet to 130 feet. Pier geometries are based on plans that were provided by our contracting partner for a bridge they had already constructed. It allowed the reuse of forms that they had on hand from that previous project. It required our design to maintain a constant 8-foot thickness with 15 feet at the top of the pier stem and the bottom of the pier cap. The width in the transverse direction varies with height at a ratio of 1:16, and at the base of the tallest pier, it is approximately 32 feet wide. An interesting note is that the RFP required a maximum slenderness ratio of 80. That proved to be challenging for non-integral piers of this height. When evaluating the slenderness ratio, we can see that there are only 3 variables that can be adjusted. L is the length of the column and was set by the site constraints and really is not adjustable. R is the radius of gyration and is a function of the cross-section of the pier. Whereas we were reusing forms from the contractor on hand to save costs, we couldn't adjust R effectively. We did look at alternatives that modified their forms, and they became much more costly than the benefit provided. Lastly, in the equation, we have K, which is the effective length constant. This is a function of the fixity of the 2 ends of the piers. For our system, we have a fixed base and a top that can move. It can rotate and it can translate. If we had a single bearing at the top of the pier, the K factor is 2.0, and KL over R was around 100, which would meet the normal AASHTO design requirement. By providing 2 bearing lines at the top, we were able to do a detailed analysis and showed it gave us some rotational resistance, and it adjusted the K from 2.0 to be closer to 1.4, and we reduced our slenderness ratio to within the contract requirements without having to modify the cross-sectional shape of the piers. This proved to be a significant cost savings to the project. The abutments for each bridge are typical gravity-style L abutments founded on an H-pile foundation. Early in the project, VTrans asked if the expansion joints could be located at the ends of the approach slabs. The reason they asked for this is it would eliminate any possibility of water leaking down onto the bearing seats and be a maintenance issue going forward. Unfortunately, after a brief analysis, we determined it really wasn't feasible given the movements that we expected and the need to use modular joints or finger joints. But as a compromise, in order to address this concern, HDR utilized a mass DOT detail, and we modified it specifically for use on this project. Essentially, we created a trough in the back wall that would be drained to an underdrain system that went in under the approach slab. So in the event of when the joints leak, and we all know that eventually joints will leak, in the events that when they leak, this water that gets past the seal would get trapped in the trough and drain away, keeping the bearing seats dry. This detail was challenging with a modular joint, and as a result, an edge beam was created to house the block out for the joint. We worked very closely with the contractor and with the joint manufacturer to come up with a detail that would work for everybody. I will now talk about a couple of other design details that aren't specifically related to the superstructure or the substructure. The original RFP had a requirement that a multi-duct conduit system be installed in one of the bridges. The design build team chose to add this to the northbound bridge because that was the bridge we were going to build first. An additional requirement was that no attachments were allowed into the bottom of the deck or to the soffit of the bridge. The design build team detailed brackets made from angles and attached them to inserts that were installed in the precast girders at fabrication. The vertical members have a slotted hole to simplify fabrication and allow for adjustment of the inserts around the post-tensioning duct. This gave flexibility in the precast plant as well as in the field. The RFP specifies the utility type and size. It required it on the one bridge, as I said, but not both. To simplify the fabrication and allow the brackets to be made the same, slotted holes are provided to allow for the adjustments in the inserts around PT. On the drop-in girders, the slots are in the top, and in the hammerhead section, the slots are in the bottom. And you can see on the slide here how we attach that to the girders and adjust them to avoid the PT duct. What isn't shown on this slide is the fact that additionally, one of the bridges was required to include a weather instrumentation system. And we chose to add conduit in the deck underneath the F barrier that are seen here in the diagram. So you can imagine on the left-hand side of the soffit, there's another set of conduits that run to the middle of the bridge that allows the owner to install the weather system after the project is complete. An additional requirement that was in the RFP was that the design must allow for the future replacement of the bridge bearings at all locations. Due to space limitations, this was a particular challenge. Seat width limitations on the abutments and on the pier heads meant that the jacks had to be placed under the diaphragms at the abutments. End diaphragms are designed with lifting in mind, so the end diaphragms of the bridge actually are designed to carry all of the load of jacking the bridge for bearing replacement. The end diaphragms were designed to be plumb after the deck is cast and reinforced to support the superstructure during that lifting. With two bearing lines at the interior pier, there's only space for single jacks between the bearings. This created a challenging placement. At the piers, the bridges are lifted actually from the bottom of the girders themselves. Now that we've discussed some of the design requirements, I'd like to spend some time and talk about design challenges that the designer, fabricator, and the contractor all had to deal with in moving this project to construction. Using the design-build project delivery method allowed for good collaboration between the contractor, the girder fabricator, and the designer. But one of the challenges for the designer were that changes were made to the girder design between the 90% and 100% submittal phases. At the request of the fabricator, optional shop bends for girder stirrups were allowed to reduce shipping heights. The bunking points, or the support points that would be used for the girders during shipping, changed from what was initially assumed based on the actual truck configurations that were available to the fabricator to ship to the project site. At the request of the contractor, stay-in-place corrugated metal forms were added at a relatively late stage in the design, and this required changes to not only the design plans, but also to the fabrication shop drawings. And as I'll talk about a little more in a minute, the bridge rail changed at a very late point in the design. So we allowed the shop bends for the fabricator, but we made a requirement that hooks that were to be installed, they must engage the bottom mat of the deck reinforcement at an absolute minimum. The hammerhead or the haunch sections are particularly challenging to design for trucking in the positive bending configuration. In their final erected state, they're in a permanent negative moment condition, and we had to evaluate the positive moment effects during the shipping configuration during the design. So at the request of the fabricator, who wanted bunk point spacings of 66 feet to meet their trucking capabilities, we found that could only be accommodated by increasing the bottom flange reinforcement to give us an increase in the allowable tension during shipping. We evaluated harp strands for a possibility to resist those moments, but it actually created problems in later stages of the erection in which we resulted in tension in the bottom of the girder. At the request of the contractor, stay-in-place metal forms can be oriented with the super elevation, and we found that to be a very useful thing for the contractor in the field. And then, as I mentioned earlier, we had to make a change to the bridge rail from our initial concept. We originally had it detailed as a Vermont standard, but we needed to make some small modifications, and FHWA rejected its use as it was not really compatible with the required 3-inch overlay without any modifications. Ultimately, we ended up bringing in an Oregon DOT TL5 barrier instead, as it had the compatibility with the overlay and with a future 3-inch overlay as needed. As I discussed earlier, one of the primary substructure challenges we were faced with was the tall columns. We discussed how we innovated and used 2 bearings to meet project slenderness criteria, but this solution actually created additional challenges for the design build team. The designer has determined that field tolerances of the pedestal heights had to be within less than 1/16 of an inch to prevent overloading of the bearings. If under one girder segment, one of the pedestals was 1/16 of an inch high and the other was 1/16 of an inch low, the transfer of additional load to the high pedestal exceeded the reserve capacity in the bearings. We didn't feel that the pedestals could be constructed to the required tolerances to prevent bearing failure, so we found an alternative solution that gave the contractor all the tolerances they needed. We included a grout pad between the bearing and the cast-in-place pedestal that was installed after the pier segments were erected. During girder erection, the haunch segments are installed first. The haunch segments are installed over the piers. The process for installing them requires the contractors to set the segments on temporary supports and adjust the supports so that the girders are installed at the proper line, grade, and profile. In order to allow the contractor the flexibility to adjust the segments as they needed, the bearings were attached to the bottom of the segments and hung in place prior to erection and until the girder was adjusted completely. Once survey confirmed that the girder was located properly, high-strength, low-shrink grout pads were placed between the top of the pier pedestal and the bottom of the bearings. I mentioned earlier that 5 out of 6 and all 4 abutments were constructed on pile foundations. At the abutments, piles are between 140 and 180 feet long. For the piers, the pile lengths varied from as little as 8 feet to 30 feet due to the sloping bedrock. This was a real challenge to determine pile lengths during the bidding phase. To make sure that the piles would develop pile tip capacities that were required, aggressive pile tips were included on all piles. Another significant challenge the team was faced with was the pile layout at the abutments. Although we designed the new abutments to fall behind the existing ones, the long existing wing walls extended into our footing footprint. As a result, we had to develop a non-uniform pile layout scheme to miss the existing piles while accounting for pile batter and the risk of pile sweep for both the new and the existing piles. On this slide, you'll see that I circled a few of the proposed piles. You may be able to notice that the pile spacing varies across the abutment. In the layout shown, the pile spacing left to right is as follows: 7 feet, then 12 feet, then several of them at 5'7", and then lastly 10 foot. This was all done to minimize the risk for the contractor having conflicts in the field. This layout was done to miss the existing piles and the existing wing wall footings that were to remain in place. I wanted to finish up today's presentation just showing a couple of construction photos that I've accumulated over the last 4 years. On the left-hand photo, you can see the H-piles being installed at one of our pier foundations. And in the picture, you can see the cofferdams and the guide formwork that is used for the installation of the piles. In the next photo over here, the piles have been cut off. The reinforcing steel is going in for the construction of the footing itself. And as I mentioned earlier, we had to put aggressive pile tips on each of our piles, and those are shown in the picture to the right. Next, I want to show a couple photos of the pier construction. What you're seeing here is the piers in varying stages of construction for the northbound bridge. In the background, you can actually see the first pier that was constructed, and it was fully completed. Pier number 2 is in the process of constructing the pier cap, and the forms are still all in place for that. And then pier 3, it's completed and ready for the cap form to move from there to here and begin that construction. In the middle photo here, it's showing the stainless steel reinforcing that was used in the pier caps. The contractor chose to build jigs and pre-tie all the reinforcing, and then they fly it over and drop it down into the pier forms. In this photo, this was taken in June of 2018, and it was the first pick that we made to set a haunch girder for the northbound bridge. As you can see, the contractor has delivered the really heavy load onto the existing steel truss bridge. It's being picked up. It'll be swung over and dropped into place. To give it some scale, that's a full-size pickup. These girders are 96 feet long, 10 feet tall, and weigh about 180,000 pounds. And the photo on the right here shows that girder up in the air on top of the pier and being supported by the temporary support that was built on top of pier 2. And then the last photo that I have is a photo that was taken a couple winters ago, where all of the piers for the second bridge were completed. Traffic is actually on the new northbound bridge, and you can see various segments of the precast girders that are in place. A couple things I want to point out is these girders go in, they get supported temporarily here. So we would put a haunch girder on this pier, haunch girder on this pier, and we would drop in these middle segments, and they get supported temporarily by this steel formwork that you see here until we do a closure port to pull them all together. And I want to thank you for your time today, and now I'll open it up to any questions you might have.